Welcome everyone for the fractional calculus seminar series. Today we have Professor Arran Fernandez, who is also the co-organizer of this seminar series. Professor Fernandez is a pure mathematician and associate professor at the Eastern Mediterranean University, specializing in fractional calculus. He completed his bachelor's, master's, and PhD at the University of Cambridge, where he began as the youngest student at the university aged 15 and came top of his year to be the youngest ever senior wrangler. Since completing his PhD in 2018, he has worked at Eastern Mediterranean University, firstly as an assistant professor and then as an associate professor. He has also spent a year working at the Sultan Qubus University, also as an associate professor. His research interests lie in connecting fractional calculus with other branches of mathematics, such as abstract algebra, analytical number theory, and Clifford analysis. His achievements in this direction include extending the Minkowski operational calculus to fractional PDE, expressing the Riemann zeta function as a fractional differintegral of an elementary function, and defining the fractional d-bar derivatives in complex and hypercomplex settings. Arran, we are very happy to have you here. You may please begin your talk.
Thank you very much for the introduction. Thank you to everyone who is here to listen. So my topic today is the Fokas method and its application to fractional PDEs. So this is a problem that I worked on quite a long time ago, in fact. So this is one of the problems from my PhD times, because Fokas, in fact, was my PhD supervisor. And he has this method for PDEs, and I extended it to a certain family of fractional PDEs, but I think there's a lot of potential to extend this to other types of fractional settings. And one of the things that I'll mention in this talk is kind of open problems, things that are not yet solved in this direction. So basically, my talk is in three parts. I will introduce the Fokas method. I have a section to introduce fractional calculus, but I will go very quickly through that because I guess in this audience, everyone is already familiar with fractional calculus. And then the main part of the talk is about how this Fokas method can be adapted and used to solve fractional PDEs. So the unified transform method, or Fokas method, it was developed by Fokas in the late 1990s. I think he won the Naylor Prize in the year 2000 for the development of this method. It's a constructive method for generating explicit solutions to initial boundary value problems for various PDEs. So it has been extended. I will give references at the end of the talk. There's a whole book that Fokas wrote on this topic. It has been used for linear PDEs and nonlinear PDEs on various types of domains and in various levels of dimensions. But what I'm going to be focusing on is PDEs in 1+1 dimensions. So one dimension of space, one dimension of time. So basically of this form, one single time derivative and a linear combination of space derivatives. This W is a polynomial, so this will be a linear combination of x derivatives to different orders of the function q. The domain for x, the space domain, is going to be a half line, can also be done on a finite interval, but again, I want to focus on perhaps the most basic case, but even in this case, it's already challenging to extend it to the fractional scenario. So I've listed a few other places where this method can be used, but that's what I'm going to focus on in this talk. So there are 4 slides, 1, 2, 3, 4, to the 4 different parts of the method. So at the top, I've put the problem that is being solved. So this is the PDE. W is a polynomial. So as I said, one time derivative, multiple space derivatives of different orders. The domain is the half line in space, an interval in time. We have one single initial condition for where t equals 0, and a set of boundary conditions that is not exactly determined at this point, because obviously it depends on things like the degree of W. If W is a linear, quadratic, cubic, quartic polynomial, there will be different numbers of boundary conditions required, and also depends on some other properties of W. So boundary conditions, I would just say TBD. In fact, we're going to solve an overdetermined problem that depends on more boundary conditions. And then at some stage, we're going to eliminate the dependence on the unwanted boundary conditions. So it's quite a nice trick that's going to be used for this. So the first step is to rewrite the PDE as a one-parameter family of divergence forms. So the one parameter is k. There is a new parameter, which is a complex variable, this k, and it's involved. So the PDE is equivalent to this identity between a t derivative and an x derivative. Obviously, this depends on the choice of capital Q. So for the left-hand side, you can see that when you take a t derivative, by the product rule, there is going to be dq by dt. There will be a t derivative of q, and there will be a wk multiplier in a separate term. The exponential factor is the same in all terms. So basically, we take the PDE, we multiply by that exponential factor, and we somehow rearrange to make it equivalent to this. Now, what is the capital Q that makes this equivalence valid? Capital Q depends on x and t and k. It's a function of three variables, and it must satisfy this identity. Okay, so that's the requirement for this equivalence, for this nice equivalence that's going to be useful for solving the PDE. So how do we find this Q? Well, what is useful is that the function w is a polynomial. So let's do some formal manipulation. We write L instead of minus I d by dx. And then on the right-hand side here, we have wk minus wl. And over on the left, we've got minus ik, and that is plus il. So there is a k minus l and a wk minus wl. We divide them, and because w is a polynomial, this quotient is also a polynomial. Wk minus wl is always a multiple in the polynomial space of k minus l. So we get a polynomial in k and l. And when we put L to be this spatial differential operator, we end up with a linear combination of x derivatives of q multiplied by some powers of k. So each Cj here is a polynomial in k, and we've got this finite linear combination. Okay, so this is the function capital Q that will be needed. And it turns out that the only place that this capital Q will really be used is where x equals 0. So when you put x equals 0, the Cj does not depend on x at all. And this x derivative of q is going to become essentially a boundary condition. So we have an x derivative of q at x equals 0 and t arbitrary. That is what is going to happen. So let's go back to this equation that is equivalent to the PDE. All right, we have a t derivative on the left, an x derivative on the right. We're going to integrate this identity. We integrate over x from 0 to infinity. That means we eliminate x. It's a definite integral, so there will be no x in the next expression. And we integrate over t, or just to avoid an abusive notation, we replace t by tau, and then we integrate over tau from 0 to t. So we end up with an identity that depends on k and t, but not x. And this is called the global relation. And this is kind of the keystone of the whole thing. It's called the global relation. It's going to be used in multiple different ways in the next steps. And this is valid for k on the lower half plane because of some conditions on convergence of integrals. Okay, we have e to the power minus ikx. So when k is in the lower half plane, this has exponential decay as x goes to infinity. If k is in the upper half plane, it would be exponential growth. So to make sure that the integrals converge, we're integrating over x from 0 to infinity. We need k in the lower half plane. Now, what are these hats and tildes? There's two different integral transforms appearing here. A hat is the Fourier transform in space. It's actually a half Fourier transform because it involves an integral from 0 to infinity. But you can see that we have e to the power minus ikx as a kernel inside the integral. X goes from 0 to infinity. And therefore, this whole thing will be like a Fourier transform sending a variable x to the variable k in the Fourier domain. The g tilde, this is more complicated. What sort of transform do we have in time? We're integrating over time e to the power wkt times something. So it's not Fourier, it's not Laplace in general. Wk is a polynomial. It's a more complicated sort of transform. Okay, therefore more difficult to invert. but it's some kind of integral transform. And we have a k linear combination. So that means a sum of these things multiplied by functions of k. And this integral depends only on boundary conditions. So we've got derivatives of q starting at x equals 0, and j goes from 0 up to n minus 1. Now, that's why it is an overdetermined problem, because we don't actually need that many boundary conditions, j going from 0 to n minus 1. We need less than that. We need about half of that. But for now, we have this expression depending on all of those boundary conditions. All right, so from this global relation, the right-hand side depends only on the initial condition Q0 and the boundary conditions, which may or may not be known, but it's only initial and boundary conditions. The left-hand side is the Fourier transform of Q multiplied by something. So by the inverse Fourier transform, we can get an explicit expression for Q. Okay, we rearrange Q hat equals something, we apply the inverse Fourier transform, and we find Q equals this. So we've got two integrals. They're both from minus infinity to infinity. The first one is fine. The first one depends on Q0. Q0 is the initial condition, which is given. It's okay to depend on that. Now, the second integral is problematic because we have this overdetermined problem. There's too many boundary conditions involved. So we want to simplify, we want to substitute, we want to change this somehow. We are going to deform the contour of integration. So minus infinity to infinity. Think of that as an integral along the real line, okay, within the complex plane. So we imagine we're in the complex plane. There's a lot of complex analysis in this method, and we're integrating along the real line, and then we're going to deform that integral into the upper half plane. Okay, we can deform it through regions where the integrand has exponential decay. So there is a domain D plus, which is in the upper half plane, depending on the sign of the real part of W of k. So if W of k is positive, then we have exponential decay. If W of k is negative, we have exponential growth. So we're going to deform through the regions that are not in D plus. This is Cauchy's theorem. Okay, if we have exponential decay, then the integral goes to 0, and you can deform through that region. So we're going to go through the regions that are not D plus until we get to the boundary of D plus. Okay, this is one of the tricky points of the method, is this complex contour integration. We start with a real integral and we go up to something else. So the shape of D plus obviously depends on the nature of the function W. If the polynomial function W is something simple like a power function, then D plus is going to be a sector of the complex plane. So the boundary of D plus is going to be two rays coming out from the origin. That's kind of what I'm showing with my hands. We start from the real line and we deform into two rays. If W is a more general polynomial, it could be something much more complicated. Eventually, this D plus shape is going to go out to infinity in two directions in the upper half plane, but what happens in between may be more complicated. Okay, so after doing that deforming, we have Q, the solution function, as one integral, real integral, minus infinity to infinity, involving the initial condition, and then a complex integral involving the boundary condition. So what's the final step? We have a formula for Q, but it's overdetermined. It depends on too many boundary conditions. We want to get rid of some of these boundary conditions by using, again, global relation. Remember, this is the global relation from step 2. This is valid on the lower half plane for K. So we're going to transform the global relation by finding a function nu. This should be a W-preserving function, and it should satisfy if K is on the contour for this integral, the new contour, boundary of D plus, then nu of K is in the lower half plane, which means that we can put nu of K instead of K in the global relation, because this is valid on the lower half plane. We substitute in nu of K here. W just stays the same because nu preserves W. That's the choice of this function nu. So all the W things stay the same, and we have something that's valid for K on this contour. Nu of K comes in the global relation, and we use these functions nu to eliminate boundary conditions. We eliminate half of them, leaving half that still need to be fixed in the problem at the start. So this TBD is approximately half of the possible boundary conditions. I hand wave a bit here because I say approximately half. Obviously, it's going to depend on whether n is odd or even, and it also depends on another subtle condition related to the function w. But basically, it's more or less half of the boundary conditions must be specified, and the other half are unnecessary. They would make it overdetermined. Now, the advantage of this method is that using these functions nu, we can choose which boundary conditions to eliminate. So, for example, if you require one boundary condition, it could be a Dirichlet problem. And then this formula is going to involve also a Neumann boundary term, Dirichlet and Neumann, and then we cancel the Neumann one. Or if it's a Neumann problem, we can cancel the Dirichlet one. We have the freedom to cancel whichever one we want, depending on which boundary conditions are specified in the problem. So when someone comes along and gives us a problem, as mathematicians, we can then figure out, which boundary conditions are desired, which ones should be cancelled, and therefore decide exactly how we should use this method. So obviously, I've given this long and complicated description in the general case. Don't know if people are still following, so I'm going to give an example to make things look a little bit simpler to see how this works in a model problem. So here's a model problem. There's only one space derivative to third order. There's one initial condition, there's one boundary condition, but I'm going to pretend that there's two more boundary conditions. I'm going to write G1 and G2 as well. So in the PDE, in the initial boundary value problem that's given, Q0 and G0 are known. G1 and G2 may not be known, but we're just going to use them and then cancel them later. Okay, so the polynomial function W is this time a cubic function, k cubed times a constant. So capital Q, remember the formula for capital Q, we've got WK minus WL over K minus L multiplied by I. So K cubed minus L cubed over K minus L. The I cancels with the minus I. And then you put L to be minus I d by dx. So you cannot divide by a differential operator formally, unless you have something like Nikosinski's operational calculus. In some settings you can, but basically dividing by a differential operator looks a bit dodgy, but we don't have to divide because we have a polynomial, k cubed minus L cubed over K minus L equals K squared plus KL plus L squared, and then we put in L and everything is fine. You've got the K squared, the KL, L becomes a differential operator, and the L squared is now a double X derivative. Okay, so this is our capital Q. This is our global relation that comes out from the, got this zoom bar, let me just move that to the top. Yes, so this is the global relation, and an important thing to notice is that the G0, G1, and G2 tilde terms depend only on minus I k cubed, that is, on W of k. So if we have this new transformation that's coming along later, the W preserving transformation, then all of those terms will stay the same. Okay, so that's step 2. We go to step 3. We go to step 3, which is the integral formula. Here, in the formula I've written, we have already deformed the contour. So Q of xt is the real integral with the initial condition and the complex integral with the 3 boundary conditions. We want to reduce these 3 boundary conditions to only 1. What is D plus? It is an infinite sector. Just like I showed in the example, you go from the real line and you deform it to a sector. So the boundary of D plus is coming in from infinity with argument 2 pi over 3 and going out again with argument pi over 3. That's what we're doing here with this complex contour integral. We need to find transformations nu such that W is preserved. Nu of k cubed equals k cubed. So obviously we use the cube roots of unity. W1 of k is omega k and W2k is omega squared k, where omega and omega squared are cube roots of unity. From the global relation, if k is on the boundary, think about it. If k is on this sector in the upper half plane, what happens when we multiply that by omega or omega squared? We rotate it. And when we rotate this sector, it goes into the lower half plane, either from omega or from omega squared. So both nu1 and nu2 map the boundary of D plus into the lower half plane. When it's in the lower half plane, we can use this global relation. Global relation is valid on the lower half plane, imaginary part of k less than 0. So when k is on the boundary of D plus, we have omega k and omega squared k are valid substitutions into this global relation. As I said, minus ik cubed does not change. So I've just written this here to remind you, G0 tilde and G1 tilde also depend on that, but this stays the same. The only things that change are the coefficients, because here there is a k and a k squared. The q naught hat term is also different, and the q hat term is also different. So here we have our omegas and omega squareds appearing. Then we substitute these. Basically, think of it as solving simultaneous linear equations. We just want to cancel out the G1 tilde and the G2 tilde. And we can do that, if we subtract these two equations, we've already canceled the G2 tilde. Then we multiply by something and we cancel the G1 tilde as well. And what we get is this explicit formula for Q, which depends only on the Q naught hat, which is the initial condition, and the G naught tilde, which is the boundary condition. We also have Q naught hat appearing again, but this formula for Q depends only on the two conditions that were given in the beginning. So this is a well-posed problem. It's not overdetermined because we cancelled out the G1 and the G2. And there's an explicit formula. Okay, it's not super explicit, it's in terms of an integral, but it's better than like an existence uniqueness result. It's not just a numerical approximation. It is something that you can write down and then you can calculate. You could calculate it numerically. And, I'm not in numerical analysis, but a lot of the people in the Fokas group are. And apparently this method is somehow efficient in terms of the numerical calculation as well. So actually calculating this explicit solution is something doable. Okay. So just to summarize, in this method, we have used transforms with respect to space and time together. Sometimes they call this synthesis of variables as opposed to separation of variables. So you cannot really separate the x and t because both the transforms are done at the same time in the space domain and in the time domain. The sort of Fourier with respect to x and this other fancy transform with respect to t. Intrinsically, this method involves complex analysis. It's a very complex analysis-oriented method. We've done a lot of deformation of complex contours, basically looking for exponential decay. We've used a lot of Cauchy's theorem, Jordan's lemma, in order to just make sure that things work out, that the things go to zero, that are supposed to go to zero, that we can deform the contours in the way we want to, that the exponential terms are not going to blow up, and so on. There's a lot of complex analysis involved here. And we've made use of the polynomial structure of the spatial differential operator. So because this is a linear PDE, we have this polynomial W in the spatial derivative, and constructing Q uses the polynomial nature of W. So when we go to a fractional setting, transforms will be okay. It's already well known how fractional operators and transforms act together. Complex analysis also is going to be okay, but it will create some problems with branch cuts when you have fractional powers. Polynomial structure, we don't have anymore. That's going to be a problem because obviously when you take fractional powers of the derivative operator, then W is not going to be a polynomial. It's going to involve fractional powers. So you can see already kind of where the problems are going to come from. And what I will show in this talk is sort of how those problems can be overcome. So very quickly, I'm going to go through an introduction to fractional calculus. Everyone knows, I guess, what is the idea of fractional calculus, defining derivatives and integrals to non-integer orders. There is this word differintegration, which is used to cover both differentiation and integration. From the applications viewpoint, which I don't know much about, because I'm not working in applications, but what little I can say about applications motivation is fractional derivative operators are non-local, so they can be used for modeling non-local processes. Viscoelasticity is a commonly cited application of fractional calculus. There's many applications in the literature, including some that are sort of not really applications. It's just people take a differential equation and substitute operators to make it a fractional differential equation, and it doesn't model anymore the thing that it claims to model. But there are also real applications that fit with real data. You just need to use a bit of skepticism when you're looking at the literature on fractional calculus. There's a lot of good papers, a lot of bad papers as well. From the pure maths viewpoint, for me, this was just a natural idea when I first learned about derivatives and integrals. We know about derivatives to orders 1, 2, 3, 4. What about in between? We get new behaviors So when you go from classical calculus to fractional calculus, properties of the operators, some things are just trivially the same. The derivative operators are still linear, for example. Some things are totally different. Classical derivatives are local, fractional derivatives are non-local. So that's sort of interesting, what happens when these behaviors change. And some things are slightly different in a way that is very natural. Like if you look at the Leibniz rule for the nth derivative of a product, and you think about how could we extend this to a fractional derivative of a product, what you would guess is exactly what actually is true. We also have new challenges. So for example, there could be some well-known method for solving classical differential equations. If you want to extend that to fractional differential equations, there are new challenges, new problems arising from the fractional setting. Sometimes this is just trivial. So there are papers where everything is just kind of, you copy and paste from the classical setting and everything works in the same way. But sometimes there are really challenging new challenges, as that's one of the things that I want to show you with this talk, how when you try to do the Fokas method for fractional PDEs, you face problems and you have to come up with new ideas to get around those problems in the fractional setting. There's various different definitions of fractional derivatives and integrals. I'm going to use the Riemann Liouville definition because we're looking at one-dimensional operators in 1 + 1 dimension space and time. So also because we're on the half line, the spatial domain is the half line 0 to infinity. I'm going to use the constant of differential integration C to be equal to 0 because 0 is sort of the special point. So here are the definitions: fractional integral, fractional derivative of Riemann Liouville type. Nu here is a complex variable, and this gives the nice property that the fractional derivative is the analytic continuation in nu of the fractional integral. So I've actually written both of them with derivative notation d, derivative to the order nu, that's the integral to the order minus nu. If nu is in the left half plane, and then in the right half plane, it's a fractional derivative. So that's the way that I think about different integrals as fractional integrals and derivatives sort of together. They're both really the same kind of thing, just via analytic continuation. So some basic properties of fractional calculus, as I said, linearity, Leibniz rule, like looking like a binomial series. Fractional integral of a fractional integral is still a fractional integral, but a fractional derivative of a fractional derivative is not necessarily a fractional derivative. Fractional derivatives are non-local. There is no simple, obvious geometrical interpretation. Here's a couple of natural examples of fractional differential formulae. When c equals 0, we have this nice formula for a power function. When c equals minus infinity, we have a nice formula for an exponential function. The well-known history of fractional calculus starts 30th of September, 1695. We just passed a couple of days ago the 330th birthday of fractional calculus. This exchange of letters between Leibniz and L'Hopital. Then there was Abel, perhaps the first application of fractional calculus. He solved the Torter-Grome problem from classical dynamics by formulating it in terms of integrals to order 1/2 and then solving it using derivatives, 1/2 derivatives. Little known fact is that as well as looking at these order 1/2 operators, Abel also looked at more general fractional operators. So there is a formula for the fractional integral or derivative, I don't remember, to order alpha in the works of Abel. And there's some translated papers of Abel on fractional calculus that are on the Abel Prize website. In the 19th century, there was a dispute between Lacroix and Liouville, who had two different ideas of how to do fractional derivatives. Formula was natural for power functions, Liouville's was natural for exponential functions, and De Morgan said that both of these may be parts of a more general system, and indeed, now this is Lacroix's formula and this is Liouville's formula, basically. So just these two guys were opposed to each other, but they were just seeing different parts of the elephant that is fractional calculus or that is the Riemann Liouville model in their case. So the same idea perhaps can be thought about nowadays when there's many different definitions of fractional calculus being proposed, and perhaps they are also parts of a more general system, just like Lacroix's and Liouville's. So, after a very brief introduction to fractional calculus, it was probably unnecessary for this audience. Here we we're going to start to think about applying the Fokas method to a fractional PDE. So here is the PDE we're going to look at. It looks exactly the same as before, but the nature of W is different. W is now going to be a finite linear combination of power functions. Wk equals this. CR constants, alpha R also constants, but now not necessarily whole numbers. They could be complex numbers. This assumption is needed for some reasons related to branch cuts. And the type of fractional derivative I'm going to use is Riemann Liouville starting from 0 because the domain of X is a half line. So in some places, I will consider just the model problem that is Wk equals a power function because fractional derivatives are linear. So if Wk is a linear combination of power functions, a lot of the argument in the general case follows from this, but it just, the expressions are much bigger. So to fit on the slides, it was easier sometimes to consider this. Now, I'm not going to go through all the details of the argument because a lot of it is the same as what I showed you before for classical PDEs. I want to focus on the places that are different, the places where going to fractional operators causes problems and challenges that were not there in the first section. So the first one of these is defining capital Q. So remember, for classical PDEs, we define the capital Q in this way. Now, W was a polynomial, and therefore this fraction, this quotient expression is just a polynomial, again, in K and L, and therefore we can express the capital Q in this form. Now, when W is not a polynomial, this doesn't work anymore. So how do we define capital Q? So I was thinking about this, as a PhD student trying to solve this problem, and one of the ideas that I came up with was to take K minus L inverse. We want to divide by K minus L. We take this and expand it as a power series, either in KL inverse or in K inverse L, according to whether K is small or large. So that's an idea. But if you just consider this sort of, this product of terms, K minus L inverse as a series multiplied by WK minus WL, that's not going to be just a series of differentials of Q because fractional derivatives do not always satisfy a semigroup property. The fractional derivative of a fractional derivative is not always a fractional derivative. So when you substitute in L as, a derivative operator, then a power of L times a power of L is not necessarily going to be a power of L. So this will get complicated. However, there is a but, and then there is another but. We don't need to evaluate this quotient. The purpose of this capital Q is not necessarily to say WK minus WL over K minus L, that's what we need to evaluate. No, the purpose of having this capital Q is to make sure that, that this equivalence is valid. So we were rewriting the PDE as this one parameter family depending on K, and we just need Q to satisfy this. That's all we need. So I decided that we don't have to follow exactly the same method of considering this quotient. All we have to do is to find an expression for Q to make sure that the required relation is still valid. It doesn't matter how we get that expression as long as we can prove that the relation and the equivalence are okay. So I did some formal manipulation. Just let's pretend that a power of L times a power of L is a power of L. And I got an expression which requires what it needs, which satisfies what it needs to satisfy. Okay, good. Next problem. The expression that I found for Q is a big infinite series. And when you have an infinite series, you need to start worrying about convergence. And in this infinite series, you have fractional operators to all different orders, like a different order in every term of the series. So what do we do with this? How do we figure out whether it converges or not? How do we kind of write this thing? Also, we don't want our problem to depend on infinitely many boundary conditions, which is what this was looking like. That would be crazy. And then another stroke of luck, looking at how this Q is used in the method, not just blindly following what we did in the original Fokas method, but thinking about why this is needed and what is needed. We don't actually use the general Q for all values of X and T and K. We only use it at X equals 0. And if you put X equals 0 in a fractional integral operator on a suitable function space, that fractional integral is going to be 0. It's going to disappear. So all but finitely many terms of this infinite series are just going to be zero. So that means the infinite series, in the case that we actually need to use in the x equals 0 case, it becomes a finite series, and suddenly you don't have to worry about the convergence anymore. Everything is kind of nice and well behaved. So more explicitly, this was the preliminary formula for capital Q, which you can see there's an infinite series here, j equals 0 to infinity. We've got fractional operators to all different orders, depending on j. We have to consider two different cases according to whether k is small or k is large. You see, when k is small, we have positive powers of k, so that we hope would converge. When k is large, we have negative powers of k. Again, we hope that would converge, but to make sure that this is continuous across the boundary between the two domains, we need to have some kind of error term to deal with the difference. So it works, but it's horrible. And when you substitute this in formally, yes, it satisfies the thing, but are we sure that this expression for capital Q even makes sense? So then there is the trick, which is you put x equals 0, and this reduces to a finite sum, and then you don't have to worry about convergence anymore. And this is on the disk for k small, but you don't have to use that assumption anymore either, because by analytic continuation, this finite sum is going to be valid for all values of k. You don't have to worry about the convergence anymore, and therefore we forget this assumption and we get a global relation that is valid on the whole lower half plane, just like in the original Fokas method. Okay, so far so good. We've done the first two steps. We've reached the global relation. Now, we've got the explicit solution for the overdetermined problem. This is step 3. And we need to figure out how to get rid of the unwanted boundary conditions. This is the domain D+. We integrate along the boundary of D+, as long as you can deform the contour from the real line up to whatever boundary contour it needs to be. And we also need this assumption on the function W, just to make sure that the domain and the deformation work in the way they're supposed to. So the fourth step is going to involve using or finding, firstly, a function nu that satisfies these two conditions. Nu should preserve W, and nu should map this contour, the boundary of D+, into the lower half plane for K, because the global relation is on this, where's the global relation? Yes, the global relation is valid on the lower half plane. So that's what we need. When K is on this contour, nu of K should be in the global relation domain. So one of the problems is branch cuts, because when your nice classical powers of K become fractional powers of K, then suddenly these fractional powers of K cannot be defined on the whole complex plane. And we're going to need to deform contours of integration through the complex K plane without the branch cuts. So we have to be careful how to define these complex powers and how to manage the complex contour deformation. So we make sure that everything uses the same branch cut, and then we make sure that we can deform the contours in a way that avoids that branch cut. So for example, if we need to rotate about the origin, turning this real line into some other contour, we always make sure that we move away from the branch cut and not through a whole revolution that would pass through the branch cut. Less than 2 pi radians might seem like something obvious, but there are complications according to the value of alpha. So if alpha is small or alpha is large, and then you're dealing with dividing by alpha and so on, this is actually a non-trivial condition. So again, more explicitly, what do we need to do? We're deforming the real axis to the boundary of D+. This is the definition of D+. What is the shape of this domain? If alpha is real, then we have rays from the origin. So again, we go from the real line to a pair of rays from infinity into 0 in one direction, from 0 out to infinity in another direction. So the deformations are the same as before, just be careful about the branch cut. If alpha is non-real, then the boundary of D+ is horrible. It consists of infinitely many concentric semicircular arcs of logarithmic spirals. So that's difficult even to draw. And then the contour deformation needs to be much more complicated. If WK is not just k to the power alpha, so when I talk about alpha here, this is WK equals k to the power alpha. If we have a real power of k or a non-real power of k. If WK is more complicated, then we cannot even describe what is this domain D plus in general? That's not a fractional problem. That's a problem even in the classical Fokas method. How do we describe the domain D plus depending on a general polynomial? We cannot do that either. So the way this Fokas method is used is not an explicit construction that works for every W. It's more like some applied scientist needs a particular problem solved. Here is the W that they have. And then for that particular W, you figure out what the domain looks like. So here's an example, just to illustrate the method again. Wk is a constant times this fractional power of k. So to define D plus, one of the conditions we need is that the following condition should be false when k is real. We cannot have this when k is real. This is equivalent to that, is equivalent to that, is equivalent to that. So when you go through all of this calculations, basically what you end up needing is this condition on alpha. So alpha must be in one of these intervals, not close to a multiple of 4. Basically, that's it. Because if alpha is very close to a multiple of 4, then you end up with some problem with the contour deformation and the definition of D plus. So there are restrictions. This is not working everywhere. Then we have another restriction. Here is the D plus. It is a sector, again, of the complex plane. It's bounded by 2 rays coming out from the origin. Just the argument is between this and that. The boundary of D plus is those 2 rays, r times a fixed argument going from infinity into 0, and then from 0 out to infinity. And we want to find nu satisfying this. And again, for some reasons, the only valid choice is this. You've got to multiply by some root of unity, sort of alpha root of unity. And this is somehow the only one that works. So we need nu to transform the boundary of D plus into the lower half plane. This is always the condition we have. And what this needs is alpha less than 7/3. So there's another non-obvious condition that is needed. So with these restrictions on alpha, let's just make a simplifying assumption. Let's say that alpha is between 2 and 7/3. This is not the only domain in which we can solve this. We could also take alpha between 5/2 and 3. I think that's also valid. Or between, there's other domains for alpha that will work. But we're only solving an example here. We're only doing a model problem. So let's fix this interval for alpha. This means that we have a valid nu that preserves W, and we also have the floor of alpha being fixed. It's 2 because alpha is bigger than 2. So here is the solution function, explicit formula with a real integral involving the initial condition and a complex integral involving boundary conditions. This is what we get from the global relation with the nu substituted. Sorry, the gamma here should be a boundary of D plus. I forgot to change that. I'm preparing the slides. And we substitute equation 2 into equation 1. Floor of alpha is 2, which means originally we had 2 boundary conditions. With this substitution, we're going to eliminate one of them, and then we have only one boundary condition that needs to be specified for a well-posed problem. So the method does work. We've got these extra complications, extra things to think about. Some things have to be done in a different way, but eventually the method does work. It does give an explicit solution for the well-posed initial boundary value problem for a fractional PDE. So to conclude, we can solve the PDE using the Fokas method with some modifications, refinements of the method. If alpha is real, this is the number of boundary conditions that need to be specified. This is very non-obvious. Where does that number come from? I can't really explain it in an intuitive way, but it turns out that that's the number of boundary conditions that are needed. This is also consistent with other things I've seen in the literature, so it does fit. The solution will consist of integrals along rays from the origin. If alpha is non-real, then there is a more complicated count for how many boundary conditions are needed, and a solution is going to consist of integrals along some rays from the origin and some arcs of logarithmic spirals. So it's going to be a very complicated thing, but it can be done. So some open problems, as I promised. What about considering, instead of a half line, finite interval as the spatial domain? Well, the problem here is that the fractional operators that I've used, the Riemann Liouville operators, they're all initialized at x equals 0. So x equals 0 is the special point. There is one special point for these operators. So if we work on an interval from 0 to L, would we need to use fractional operators, for example, left-sided starting from 0 and right-sided starting from L? How would they fit together? I tried to do this. This was another problem that I tried to solve during my PhD, to extend from the work I had managed to do. But I failed to get anywhere with this. I always feel it's something I should come back to one day, with more maturity and more advanced knowledge of fractional calculus. Maybe now I could figure it out. Other types of fractional PDEs, I've just used Riemann Liouville operators. What about, for example, fractional Laplacian on a different sort of domain? What about Caputo derivatives or other types of fractional derivatives? What about nonlinear PDEs, which could also be solved by the classical Fokas method? Nonlinear fractional PDEs, who knows? Again, there are, of course, challenges. The properties of, if you use different operators, they will not work in exactly the same way with the Fourier transform and so on. We might need different transforms, maybe different properties in the complex plane, and, extra challenges would come up. Explicitly, the only solution we have is in the case of wk equals k to the power alpha, just this power function. So what about if you have a more general linear combination of fractional power functions? Well, even in the classical Fokas methods, there is no explicit solution for the general polynomial, because even finding the function nu that preserves w for a general polynomial w, there's not a nice formula for that. Like imagine solving a quintic, it's that sort of problem. So what we need to do is to find some specific problems that have applications that are in the form that this method can solve. And then, as always, if some applied scientist has a problem that needs solving, they can bring it to me as a pure mathematician and I can figure out what to do to solve it. But firstly, I need to find someone who actually has a problem like this that needs solving for a fractional PDE. So here's a bibliography. The first reference is from 1997 when this method was first published. The second reference is the book of Fokas about this method in many different scenarios. So it's a nice book to learn this method from if you want to read more deeply. Then there's three standard textbooks on fractional calculus. I guess this audience will already know them. There's a paper of Kaikina, which I found while I was working on this problem, that actually solved a similar problem by a similar method, but not exactly the same. So it was interesting to compare. And then the one in red is my paper that this talk was based on. As I said, it's from quite a while ago. It's from 2018. So I had to sort of revise this in my memory before giving this talk. So I hope that the time is okay. I will stop there. Thank you for your attention.
Thanks, Arran, for the nice talk. For questions, please raise your hand. I'll call out your name in the order that they appear on my screen. Yes, Professor Luchko.
Hello.
Hello, Arran. Thank you very much for a very nice presentation, for a very nice talk. And thank you for making us aware of the Fokas method, because also for me it was a new method. I didn't know this method before. As you probably know, a big part of PDEs theory concerns with functional spaces. I mean, for different types of PDEs, one looks for suitable spaces to guarantee existence or uniqueness of solution, to guarantee that certain methods work. And in your talk, you didn't mention any functional spaces. I mean, of course, today you had just very few time, but the question is if this point was already somehow resolved by using the method. I mean, formally everything works well, but the method contains a lot of formal manipulations that should be probably justified in certain functional spaces.
Yeah, that's a great question. Thank you. I don't actually remember, it's the honest answer. I've got this paper in front of me from 2018, but I don't remember if we discussed function spaces there, and we may not have done, because as far as I remember, even when I learned this Fokas method in the non-fractional setting for classical PDEs, there was not much talk about function spaces, maybe because the viewpoint was more sort of very applied mathematician style, and they're not just existence uniqueness, which wouldn't make sense without a function space, but it's actually constructing a solution. So it was more like, as long as this works, if the integral converges, then everything is fine. Probably there is at least a complex differentiability assumption somewhere in there, which of course is quite a strong condition, because Cauchy's theorem is being used, Jordan's lemma, to deform the contours of integration and so on. But I don't know what other conditions might be needed, if any, on the Q0 and the G, like the initial and boundary conditions. But yeah, maybe sort of should be looked into to make this method more sturdy.
Yeah, I can imagine that in the fractional case, this could be a very, very difficult problem. But as you mentioned, even in the classical method of Fokas for normal classical PDEs, this point was not discussed extensively, you mean?
Probably it has been somewhere in the literature, but not in like the course that I took from Fokas, and maybe it's in his book, for example, that I mentioned on the previous slide. Maybe there's some discussion in there about function spaces.
Okay, thank you very much.
Thank you.
Are there more questions? You can unmute your mic and go ahead. I guess no. So I think this is a good point to close this talk here. Thanks, Sharon, for the nice talk. It was nice having you here today.
Thank you very much.